Hi everyone. Today I want to solve this FE exam heat transfer problem for you. We're going to solve this problem step by step and really focus in on those fundamentals. The real fundamental to this problem is understanding energy balance and heat exchangers. Heat exchangers in particular is a super important topic for the FE mechanical exam since you can see it's explicitly called out in the reference, subsection E here under the subject heat transfer from the FE exam specification. We're going to go ahead and read through this problem and try to understand exactly what we're looking for. So it says hot oil flows through a well-insulated heat exchanger at a certain mass flow, and it's cooled by water that's entering and exiting, and we're given the temperatures, and it's flowing with a certain mass flow rate. We're given specific heat information for both the oil and the water, and also the total heat transfer area. We're looking for the overall heat transfer coefficient here. It's measured in units of power per unit area per temperature, which is a unit like a heat transfer coefficient. Or a unit like a convection coefficient. And let's go ahead and write down some of our inputs here. By the way, you can try this problem for yourself using the first link in the description below. Let's go ahead and write down these inputs. So it says hot oil, which is, I'm going to label this bottom kind of input as oil. And you can see that we have a counterflow configuration here. The oil is flowing rightward while the cool water is flowing leftward. So that's a counterflow configuration there. The hot oil I'm going to label as this bottom stream, 212 degrees Fahrenheit inlet, and we're unsure of what the exit temperature is, but we understand that the mass flow rate of that oil is equal to 17.6 pound mass per second. We also know some things about the water. The water enters at a temperature of 68 degrees Fahrenheit and exits at a temperature of 113 degrees Fahrenheit, and it's flowing at a mass flow rate of that water is 22 pound mass per second. The specific heats they're given, CP of water is 1 BTU per pound mass degree Fahrenheit, and the CP of that oil is 0.478 BTU per pound mass degree Fahrenheit. And the total heat transfer area, the A, is equal to 129 square foot. And we're looking for the overall heat transfer coefficient. Usually that's denoted by variable U. Okay, so we have a heat exchanger here. Let's go ahead to the heat exchanger section here in the FE exam reference manual. On page 215, under the heat transfer subject, you can go ahead and find this heat exchangers section here. And we're given some things about the heat transfer that you can find from either the hot fluid or the cool fluid. And that's just MCP delta T. We're also, you can see that U term that we're looking for, the overall heat transfer coefficient. And we can find that using the heat transfer rate, which we can calculate, right? We know the temperature in and out of the water, for instance. We know the CP of the water, the mass flow rate. We can calculate that Q dot. Is there anything else in this equation that we don't know? I'm looking at this log mean temperature difference here. We don't know that. And yeah, that's pretty much the only thing we don't know. So the entire problem kind of hinges on finding that log mean temperature difference. And for the counterflow configuration, the log mean temperature difference is a function of your inlet and outlet temperatures. If you recall, we don't know the outlet temperature of the oil. Now, this is where the idea of energy balance comes in. What you can kind of think about here is our goal is to find this temperature of the outlet of that oil. And the way we can find it is by energy balance. Also, we can note that the heat transfer loss from the oil is the same as that gain from the water. So we could state that the heat transfer rate is mass flow rate times Cp times delta T of the water. And we could state that that's equal to mass flow rate times Cp delta T of the oil. We could do that. I want to show you where it comes from in the first law to really hammer in those fundamentals. So if we start off with the first law for an open system, which says that heat transfer minus work is equal to the change in the enthalpy of the system plus change in kinetic plus change in potential energy. Let's get rid of the rates for now. What we can note is that if we take our system to be the entire heat exchanger here, we can note that no heat transfer is going to occur outside of the system. There'll be no heat crossing the boundary of this system because everything's happening internally. So the heat transfer is going to be zero. There's only internal heat transfer. There is no boundary work or other forms of work mentioned in the problem. There's no speeds or height changes, so the kinetic and potential energy changes drop out. So what we get is essentially that the enthalpy change of the oil is the same thing as the enthalpy change of the water. And if we take a time rate of change here, what we can see is that mass flow rate times the change in enthalpy of the oil is equal to mass flow rate times the change in enthalpy of the water. And those are those respective mass flow rates for oil and water. CP could be computed by a enthalpy change can be computed by a CP delta T term. So if we substitute that in here, what we get is that the mass flow rate times the CP times the delta T of the oil is the same thing as that of the water. Okay, so this is where it comes from the first law. And additionally, we kind of understood that the heat lost by the water is gained by the oil. So what's our plan here? That equation that we were looking for before, the heat transfer rate is equal to the overall heat transfer coefficient times A. I know there was an F here, but they said if no information on F was given, set it equal to 1. So we're going to leave it off, multiply by delta T of the log mean temperature difference. So what I'm thinking here is that this log mean temperature difference is a function of all of the inlet and outlet temperatures. So using the water flow, we can compute the heat transfer rate. That's just the mass flow rate of the water, that's 22. M dot Cp delta T of the water is what I'm plugging into. Mass flow rate of the water is 22. Cp of the water was given as 1. Delta T of the water is 113 minus 68. 990 here, and that is pound mass per second. The 1 was BTU per pound mass degree Fahrenheit, and this is degree Fahrenheit here. We work out the units quickly, we get a BTU per second here. And we know this is exactly equal to the heat gained. The heat lost by the oil is equal to the heat gained by the water. So that 990 is the same for m dot Cp delta T of the oil. And we can use this to find what the delta T of the oil is. We just take the 990 and divide it by the mass flow rate of the oil. That's 17.6. And the Cp of the oil is 0.478. It was given above. Before we solve the rest of the problem, if you're enjoying this video and you're learning something, consider leaving a like and subscribing for more content like this. Additionally, if you're prepping for the FE Mechanical exam and looking for a resource that will help you pass, consider checking out my software, FE Interactive. It's the third link in the description below, and it'll give you access to multiple different sections, practice exams, review and improve sections, as well as a tips and tricks section, which helps you use your calculator better and save time on test day. An analytics page, which ties all of the different pages together. You get data for each of those pages, where you can view, for instance, how you did on each exam, as well as a detailed solution manual for each exam, so you know exactly where you're making the mistakes, what exactly is the misunderstanding coming from, and all of those are tied together with an overall data point. The overall data point can be reorganized in terms of performance so that you know what are my top 3 subjects, what are my bottom 3 subjects. Having this kind of data is super valuable since it helps you isolate your weaker points and fortify your strong ones. I'm confident that my software, FE Interactive, will help you pass the FE Mechanical exam. And again, you can check it out using the third link in the description below. You get 2 months of access for $9.99. Let's get back into the video. 117.67 here. So note that the delta T of the oil is that amount. As we're flowing through that oil section, you can see the temperature is going to be decreasing because the water temperature is increasing. The oil is giving some of its heat away, and that's causing the oil temperature to decrease and the water temperature to increase. If the temperature is going to decrease, that means we just do 212, subtract off that delta T of 117.67, and what we get is 94.32 degrees Fahrenheit. So 94.32 degrees Fahrenheit is this. Now we can go ahead and plug into the log mean temperature difference, and we're almost on our way to solving this problem. I'm going to go ahead and screenshot for a counterflow heat exchanger what the delta T log mean is. We're just going to plug right into it. Okay, so what we have is the hot outlet. See if I could bring this into view here. The hot outlet, the hot stream is the oil because it's coming in at a hot temperature. The hot outlet is 94.32. That's what we just computed. The cool inlet is the cool inlet of that water, 68 degrees. Subtract off the hot inlet is 212. That's the hot inlet of the oil. And the cool outlet of the water is 113. Divided by, you can see these terms in the numerator are identical to the numerator of this ln term. So it's just 94.32 minus 68 divided by the other term. 212 minus 113, and we take the natural log of that. This is how we compute the delta T log mean, equal to 54.86 degree Fahrenheit. Actually, yes, this is correct. What you could see here as well is that since these are delta T's, we don't have to convert it to Rankine here because that delta would just cancel out for both of those conversions, that factor of 459 here that we add onto the degree Fahrenheit. Okay, let's finally plug into that upper equation. The fact that the heat transfer rate is equal to U A delta T log mean. We have the log mean temperature difference. We just calculated. We know what the heat transfer is. We know what the area is that was given as 129 square feet. So we can go ahead and calculate U. That's Q dot divided by A delta T log mean. Q dot was 990. Area is 129. And delta T log mean is 54.86. Let's see what kind of units this is going to come out in. We know that 990 was BTUs per second. The 129 is foot squared. And that last term over here is Fahrenheit. I know that the choices that we had were BTU per minute, foot squared degree F. So what I'm going to do is multiply this by a 60 seconds per minute here to convert that denominator to minutes. So we'll just multiply this by 60. Overall heat transfer coefficient of 8.4 approximately BTU per minute, foot squared degree Fahrenheit. Let's go ahead and check this answer. What we're getting here is pretty much 8.4. I checked that answer. I did get it correct. And if you enjoyed the video, consider leaving a like and subscribing. Additionally, if you don't have a lot of time to solve these problems, definitely check out the first link in the description below. You can access this entire page with a bunch of different problems that we've solved, and you can go ahead and filter through all those problems with the different subjects, different difficulty levels. So you can go ahead and try that out if you don't have enough time to watch the video. Thank you for watching. I'll see you in the next video. Goodbye.